Welcome to this demonstration of Autodesk Nastran in CAD. During this video, we'll discuss design validation for industrial machine design. The machine you see here is used to fill consumable products in cups. We're going to focus on the end of the design where the product is sent for packaging. The upper portion of this subset is made up of a vacuum system that lifts the cups by the lid and transfers them to the box. The lower portion translates the nest up and down via rack and pinion to support each cup. Let's take a look at this subassembly in its own window. The current design seen here has already been built and tested. Due to demand for higher capacity machines and increased throughput, we're making a change to this design to move more product per cycle. The changes, of course, can be made right here in the design environment. We'll add 7.5 inches to the length of the bar. Back in the assembly, you can see the new design. The question, of course, is, will it work properly? Let's run an analysis to find out. We only need to show a portion of the model to validate the design integrity. You can see that Autodesk Nastran in CAD is fully embedded in the design environment. There are several types of studies that can be solved, as opposed to Inventor Professional, which is limited to linear, static, and frequency study types. In this case, we're going to progress to a dynamic study since the parts are moving at high speeds. First, let's find out what the resonant frequencies are using normal modes. Solid elements or shells can be used in this case. We'll use shell elements, choose the material, and specify where it is used. The current thickness of the model is 1/4 inch. The mesher will apply quad surface elements to the selected faces. Next, we'll properly hold down the part, similar to how it's held down in the assembly. There are several options available for doing so. On one end, we'll leave the X direction free to rotate. And on the other end, we'll do the same thing, except we'll leave the Y direction free so the part doesn't become over-constrained or too stiff. We'll use a welded contact between the parts. Bolted connections is another option, but we are mostly interested in the behavior of the bar stock. And we'll solve for the first 30 mode shapes and their frequencies. The solver only takes about 30 seconds to complete. We can then take a look at the areas in the model that have the least amount of stiffness and how it tends to vibrate. We can see the first mode is 48 Hz. Let's keep that number in mind. Each mode includes the option to play an animation of how it moves. This display is exaggerated, making it easy to visualize the behavior. The pull-down shows all 30 modes that were solved, so we can view and animate higher natural frequencies in the design. This one happens to show the participation of the C channel at 165 Hz. There is another boundary condition that we haven't considered. It's the mass of the objects that are attached to the bar stock. All 36 of the locations have been selected and given a mass value. This is a huge time saver as opposed to meshing all the parts with solid elements. Let's accept this and run the solver again to see the impact. The first natural frequency is now down to 17 Hz with the added mass. This may be a concern since the model tends to vibrate in the same direction as the motion in the machine. We can dig a little deeper by applying the actual velocity or acceleration to the model. Let's change the study to a transient response type. When adding the load, there is now the option to enforce motion and specify displacement, velocity, or acceleration. We'll choose both ends of the C channel and input variable speed over time using a table. We want to find out what happens when the model comes to a sudden stop. There are several options for damping, which we'll include in our study. And finally, determine the amount of steps we would like to record. Basically, we're taking a picture every 0.03 of a second 50 times. Now we can run the solver, which takes about 2 minutes. Let's start with an animation. We're going to include all 50 time steps. Feel free to choose from several result types to view during the animation, and specify the range for the legend. Animations are nice, but what about the numbers? XY plots collect the data from all 50 time steps or a given range. We created a group earlier by selecting an endpoint on each of the bars on one side. You can see what happens when the model stops. It vibrates over 1/8 of an inch, and that's not good for the vacuums that are trying to grab the cups for packaging. Let's make a change to improve the design. Since we're using shell elements, we can change the thickness of the bar stock in the study. We'll double it from 1/4 inch to 1/2 inch, and run the solver. Back in the XY plot, we can see that the displacement is down to less than 0.04 inches, and you can also see the vibration beginning to dampen out in this graph. This is a reasonable result for moving forward. All we need to do now is change the thickness of the model, and once again, this is all done in the CAD design environment. Autodesk Nastran in CAD is robust, easy to use, and is part of the Autodesk digital prototyping solution.